Welcome to the first workshop seminar of the summer. It's our pleasure to have Tobias Scheffer here. He's coming to us from the Max Planck Institute at Saarbrücken. He's the head of the machine learning group there in the CS department, which is the Max Planck in Saarbrücken. He finished his PhD in '99 at the Technical University of Berlin. Since then, he's worked at Siemens in New Jersey, the University of New South Wales in Australia, the Technical University of Berlin, University of Magdeburg. He was a research professor at Humboldt University, and now, of course, he's the head of the machine learning group at Max Planck Institute. So he's going to talk to us today about a talk actually that I was lucky enough to see about a month ago. It's very interesting. Without further ado, Mike.
Thanks very much for the kind introduction, and thanks to Keith and Sanjeev for having me here. It's great to be here at Johns Hopkins. So I'm going to talk about learning under differing training and test distributions today. The storyline is basically that machine learning algorithms are based on the fundamental assumptions that training data is available that has been drawn according to the same distribution that the machine learning system will later be exposed to at application time. And this assumption is really built deeply into the machine learning algorithms that we use today. Unfortunately, it's an oversimplification in many areas, such as including spam phishing or learning problems that for which standard corpora are used for training that in many cases don't really reflect the later intended use very well. So I'm going to present an integrated optimization criterion that is correlated to good performance of a classifier system under the test distribution, and that can directly be maximized based on the available training data, and it doesn't really require to explicitly model the training and test distribution, and we'll have a look at how this works empirically for a few problems. So the assumption that a classifier is exposed to some test distribution and that training data is available, drawn from that very same test distribution, is built quite deeply into all the classification algorithms that we use today. And there's quite a selection of cases where this just isn't the case. For instance, in very many applications, the test distribution simply varies over time. If you happen to have looked at the Netflix competition, the task there is to predict how much people are going to like a particular movie based on how much they have liked movies in the past. You will observe that the distribution of scores varies over time dramatically. Movies just become less popular and new movies become popular and trends change. So if you just learn from the past training data, this is going to tell you a little bit about the future, but not as much as you would like it to tell you. There are also quite a few applications where test distributions are purposefully altered. If you look at spam or phishing emails, people look at how current spam filters work, and then they change the distribution of the spam emails which they send, such as to render the current spam filtering hypothesis useless. So for instance, people use these good word attacks. They insert phrases or words that reflect good emails as closely as possible into spams to change the distribution of spams. Or they come up with entirely new techniques, such as animated GIFs, which haven't been in the training data that has been used for learning filters. So they probe existing filters and then purposefully change the current distribution of instances such as to render the hypothesis useless. In language processing, standard benchmark corpora are frequently used for training. If you want to have a parser that, for instance, parses biomedical papers, then in many cases you would use something like the Pan-Tree Bank in order to train the parser. And I mean, the concept of English grammar doesn't fundamentally change from the Pan-Tree Bank to biomedical paper, but the distribution of input patterns is just fundamentally different between different application areas. So the target concept in a way stays the same, but the distribution of inputs that get observed by the system changes. And so by learning from the training data that comes from a different application domain, we're kind of optimizing not quite the correct criteria. Finally, there are quite a few applications where the distribution is very user-specific. Back to spam, there's this collection of public training corpora, such as the Enron corpus, that contains emails received by managers of the Enron Corporation, or spam assassin data. This is quite frequently used to train spam filters. And those spam filters may not work so well for someone who does not happen to be an Enron manager. Someone who just gets a different distribution of emails gets exposed to a filter that has been trained from quite a different distribution of emails. So in a way, this is not the right thing to do. So the problem setting that we're really interested in is that there is a collection of test data, and this test data is governed by some distribution theta of instances. The test data, of course, is unlabeled, and the goal would be to find the correct labels. And this amounts to minimizing some expected loss defined with respect to the test distribution theta. And that's what we want to do. In order to achieve this, usually, right, the expected loss is defined with respect to the test distribution. And in order to achieve this, we usually have some labeled training data, but this training data is governed by some distribution lambda, and usually it's a completely different distribution lambda. A nice assumption is to say that the target concept stays the same. So the conditional distribution of the class variable, basically the target concept, we assume this to be the same for the training and test data. So it's not like from the labeled training data we're trying to learn a completely different concept. We are trying to learn the same concept, but with respect to a different distribution of underlying instances. So training and test data have different distributions over instances, and the goal is to minimize the expected loss under the test distribution. So an obvious thing to do, an obvious baseline, would be to simply learn from the training data. You can always do this. The training data are labeled. You can just learn and classify on the training data. By doing so, we would basically use an algorithm that minimizes the loss then with respect to this training distribution. So we minimize some expected loss with respect to lambda, and that's the wrong criterion.
Excuse me? Could you unlock one slide?
Sure.
So the conditional, I would say, P of y given x, y is the class, x are the feature.
Right.
But it's the marginal on the features that change. Is the only thing.
P of x changes.
Yeah.
P of x given either lambda or theta, that's different. Exactly.
And I can sort of see why this may be true in the spam case, because the different users will have a different sample X which they consider not spam, but the spammers, I presume, spam everybody with the same thing.
Mm-hmm.
And so there, I suppose P of y equals spam given X is the same.
Mm-hmm.
But I'm trying to see whether P of y given X for X not spam is also the same.
It's a problem setting.
Okay.
It's not the only conceivable problem setting. There are possible applications in like multitask learning where you want to learn possibly in some way related concepts that are still distinct.
Okay.
And this is not covered by this problem setting.
Okay. All right. I'll revisit it later then. Let's go through it.
If you want to learn from the training data about some target concept with a different distribution of the class variable, then this data doesn't suffice. There are problems, there are applications where you have other kind of data. And,
Okay.
but this is basically one possible problem setting for which the marginal distribution of instances changes, but the class variable statistics, yes.
In this case, you're just assuming that you know P, right?
No.
So you're assuming that you know the form of P.
No,
you just don't
absolutely
know
not. No.
zeta and lambda.
No, absolutely not. I'm just assuming there is a training distribution and there is a test distribution.
And they are the
but
same.
they are different.
No,
and
P
unknown.
and P, right? You're talking about the same P, but different lambda.
P is
zeta.
just the symbol for probability. So there is a probability for the instances under the training, in the training data, and there is a probability of instances in the test data. They're not the same, and they're unknown. Nothing is known about them.
Nothing is known.
Nothing
P
is
is unknown, and theta and lambda are unknown.
Exactly. Everything is unknown.
So the form is not assumed, right? You're not assuming it's log linear or...
No, nothing assumed.
So it's the theta and lambda are very generic index set. They're not parameters where you just change a value. Okay.
Nothing is known about them.
Yeah.
Mhm. Yes?
One more thing to make it. So what you want to learn in a classification task is really the conditional P of y given x, because you're going to observe an x and you want to know P of y.
Yes,
So,
something like this. You want to have a classifier that takes an x and predicts a y.
yeah, but that's a function of P of y given x. That's in classification. This is what you want to. You don't want to learn the marginal x.
No, you don't want to learn P of
classify,
x.
so to know P of y given x. This is what you want to know.
Yes, you want to know this.
So it's the same in this case in the training and the test. So
But
okay,
still-
I understand that the marginal index is not the same, but in principle the classifier should not care about it.
Yes, the classifier has to care for it, because the classifier has to minimize the loss with respect to some distribution over x.
Yeah.
Okay,
so
so
you want
assume that under the training distribution, there's a high probability of +1 on this side of the blackboard and a very small probability of -1 on this side of the blackboard, and a large probability of -1 here.
yeah.
Okay, let's.
Yeah.
That's okay. As soon as you write down the loss,
I
it's
see,
clear.
yeah.
Okay.
Okay, what happens? So if you get P of y given x, exactly correct. Actually, we don't care. But what it is that you want to put energy on region where x are very likely, and this is where you want your classifier to be good.
Exactly. If under
And
if
what
under the
happens is
training
that it's not the
distribution,
same.
if there is a region under the training distribution that becomes sort of unlikely under the test distribution, then it's not important what the classifier thinks about this region. So the classifier kind of has to focus on being right for those instances that actually occur under the test distribution with a high probability. And it
Yeah.
can be wrong for instances that have a low probability.
All right.
So the classifier in general is the optimal classifier under the test distribution in general is quite different from the optimal classifier under the training distribution, even though the conditional is constant.
Yeah.
If you restrict the space, if you restrict the hypothesis space, right?
In general,
Well, if you are always just if the capacity of your classifier was enough to be able to exactly model the true P of y given x.
plus you had infinite training data. Even if the
Yeah, well, hang on. We weren't talking about training data with response to Bruno's question. We were just talking about whether the optimal classifier would care, regardless of how you got it.
Okay.
Of course, the real problem is getting it from
if
the training data on the right.
If the capacity of the classifier is large enough or is
Yeah.
infinite, then there is an optimal classifier that works for either distribution.
Yes, I think that was his point.
But given finite amount of training data,
You can't find it.
you can find it.
Yeah.
And finding as good as possible a classifier under the training distribution is in general different from finding as good as possible a classifier under the test distribution,
Exactly.
given finite data.
Excuse me, what Bruno said is correct, assuming that you have not criteria, match posteriori classification. In that case, you only need the posterior distribution, y given x. Otherwise, if you have a general loss function, it is not obvious why you only need that. Obviously, you need the whole joint distribution, which makes this problem interesting. But if you're only interested in classifying classification, for example, you have y just takes some discrete values, and you're only interested in minimizing error, then you only need the posterior distribution, y given x.
The loss function only
how
pays
are you-
attention to y.
So what I'm saying is that you only want to find the distribution of y given x.
Yes, and how are you going to find that? You're going to minimize some criteria to find it, right? And
Assume if you knew the correct distribution
if
of
you
y
knew,
given
then
x.
you won't
If you knew the distribution, then there wouldn't be a problem.
That's what I'm
Excuse
saying,
me,
that in order
he has stated his problem. Why are you arguing with it?
I mean, it makes sense to wonder whether this is a trivial problem.
And
or
he's
something.
now going to tell us how he solves the problem he's doing. You can have your own problems.
We all have our own problem.
No, I mean, it does make sense to want to wonder whether this is a trivial problem or something.
No, it's certainly not trivial. No, nobody's. We all want to hear how you solve it. Please tell us.
Yes. Let's go on. Let's go on.
Do we agree that it's a non-trivial problem?
Yes.
Yes. And Dominus, you have the next hour with him to explain to him your problem.
Right. Okay, so training from the training data will in general minimize the loss with respect to the training distribution or whatever this training algorithm does. Whatever it minimizes, it's going to minimize this with respect to the training distribution. In general, this is going to be different from minimizing the same thing with respect to the test distribution. So this baseline doesn't work very well. So now let us, for 1 minute just, let us assume that the training distribution and the test distribution were known. And this is just an assumption for like the next 3 minutes or something. In general, they're not known. But if they were known, then with the instance's test probability over its training probability. Okay? The expected loss under the test distribution of the classifier for an instance, expected over all instances, can be rewritten as expected loss under the training distribution, and the loss incurred for every instance has to be rescaled according to the test distribution over the training distribution. So we just would have to we would have to weight the loss incurred for each instance by this ratio, right? So we minimize this, and we're fine. Problem is, neither training nor test distribution are known. So in order to illustrate this a bit more, assume that the blue curve is the test distribution and the red curve is the density of the training distribution. And for x sub 2, we have the distribution under the density under the test distribution, and the test probability is 3 times higher than the training probability. So by intuition, the loss incurred for this instance on the training data has to be weighted by a factor of 3 in order to reflect the loss under the test distribution. So this instance is 3 times more likely to occur under the test distribution and under the training distribution. The loss has to be scaled upwards. On the other hand, for x sub 1, the probability under the test distribution is 0. The probability under the training distribution is greater than 0. So basically, whether the classifier performs well or not, for this instance, it doesn't matter. So the loss on this instance can be scaled down to 0. So the problem is solved if we knew training and test distribution. And to write this there's a version of this equation written with probabilities. It's kind of similar. The log likelihood of the training data, sort of under the test distribution, is a sum of the log likelihoods of the individual instances, where the log likelihood of each instance is weighted by the same ratio of test distribution under training distribution. So this loss can always be interpreted as a log likelihood. And if we're interested in discriminative training, as opposed to model-based training, then the log likelihood of each instance would be the log likelihood of the class variable given x. And each of these guys would have to be scaled by the same factor. Okay, so now let's not forget that these distributions aren't known. Probably the most straightforward approach to this problem then is this algorithm by Shimodera. And it proceeds in these 2.5 simple steps. It first estimates the training distribution from the training data using kernel density estimation. It estimates the test distribution from the unlabeled test data, again using kernel density estimation. And then it goes on and minimizes some regularized loss. And for each instance, the loss is weighted by this estimated ratio of test distribution over training distribution, plus whatever regularizer the algorithm likes to use. This algorithm basically works. It's got a number of issues. First of all, potentially very high dimensional distributions, the training distribution and the test distribution have to be estimated from the data. And that's quite a difficult problem, And the problem is actually much more difficult than it needs to be. Because these distributions in the end aren't really needed. All that's needed is a correction weight for every single trading instance and not the full distribution over instances. And also, it heuristically decomposes the ultimate problem into two sub-problems. First, the sub-problem of learning the correction weights by means of estimating this density. And for this first learning problem, some criterion is optimized that's pretty much decoupled from the classification accuracy, which we want to maximize in the end. And second, learning from the weighted data. And decoupling a problem into two problems that are being solved sequentially, that kind of leads to the error rates in each step adding up. And also, for the first step, what optimization criterion should be maximized? We don't really want to know these distributions. So whatever we do maximize is kind of decoupled from what we actually want to do. So here comes an approach that doesn't have these issues. It does not estimate these distributions, and it does the entire optimization in one step and only maximizes the expected loss or minimizes the expected loss under the test distributions. And this is how it works. We have the training data, the training distribution, the test data, the test distribution, and here is another random variable, sigma. Sigma indicates for each instance whether it's a training or a test instance. For all the training instances, sigma equals 1, and for the test instances, sigma equals 0, and sigma is an observable random variable because for every element of the training data we know sigma is 1, it's their training instances, and for the test instances we know sigma is 0. So the random variable sigma indicates whether x has been drawn from the training distribution or from the test distribution. And we can read the probability that sigma equals 1 given x and given the training and test distribution as the probability that x is a training instance given that it has been drawn from an urn that contains all the training and test instances. So P of sigma equals 1 is the probability that x is a training instance given that it's either a training or a test distribution. So the probability that governs sigma describes the difference between training and test distribution, and only the difference between training and test distribution. It doesn't tell us anything about the training distribution or the test distribution, but it completely characterizes the difference between the two guys. So it's a completely discriminative probability, it's a completely discriminative model. Plus, we have all the data needed in order to find a description, in order to learn this model of the difference between the two distributions. We have the training data and the test data, and that is basically the information needed in order to learn a model that predicts for every element whether it is a training or a test distribution or something in between. So we can learn a parametric model, P of sigma equal 1, given x and given some set of parameters that basically takes as input an element and as output gives us the likelihood that this is a training instance as opposed to being a test instance. If these distributions are equal, training and test distributions are equal, then this model would just be a flat line. For every instance, it would give us some constant probability of the thing being a training or a test element. But if the distributions differ, then this model could tell us that a particular instance looks rather like a training instance, whereas some other element looks rather like a test instance. So we can learn a model of the difference between training and test distribution with some set of parameters. Agreed?
And then the correction factor that you are looking for, the scale would be a likelihood ratio under this model.
Almost. Pretty close. The correction factor we're looking for, this guy, is some constant factor times 1 over this, this probability minus 1. So this theorem says that from this model that discriminates elements into either training or test, we can immediately calculate the ratio of test distribution over training distribution. And the significance of this is that in order to only get the correction weights, there's no need to actually learn the individual distributions. It suffices to have a model that's able to discriminate between the two distributions. We don't need to do any model-based training. We just need to be able to tell the training data from the test data in order to derive these optimal correction weights. That's the point here. So the elements of this framework are training and test distribution, of course, and the model that discriminates training versus test elements. From this model, we can derive the correction weights, the test to training ratio, as constant factor times 1 minus the output of this training versus test model minus 1. And so we can basically assign a training weight to each of the, we can add a significance weight to each of the training instances. And then basically we can imagine that we can learn from the weighted training data and then find a hypothesis that doesn't look so well for the actual training data, but since it works for the weighted training data, it will then work for the test distribution very well. This model will have another set of parameters, W. So all the parameters that are in the system are this vector V and this vector W. V characterizes the difference between training and test distribution. W is the final classifier. V leads to the weights for the training data, and the weighted training data somehow will lead to the resulting classifier W. But, yes?
On the left-hand side of the equation, there is no V, and on the right-hand side, there is a V.
Yes, true. The equation, the original equation says the ratio of this distribution is equal to this probability. And this probability again depends on the training and test distribution. And this, of course, we don't know. But for this distribution, one can learn a model with parameters V. And V is the set of parameters for the model that we learn for this. So this is the true distribution, and this is the model for this distribution that can be learned by discriminating training versus test data. So from this parametric model, you can maybe put a head over this or something. From this model, we can come to the weights that we assign to the training data.
And
But this isn't an algorithm yet. These are just the elements of the framework, and now we have to ask, how can we actually find all these parameters in a way that makes sense? So how can we find sort of the best W and sort of the best V, and how do they interact?
And what about the constant error? That's the size of
This is the size of the training data versus the size of the test data. Actually, if the training data is 10 times larger than the test data, and you draw from an urn that contains all the training or the test data, with 90% probability, you're always going to draw a training instance in this kind of. But this is just a constant factor. It doesn't really play a big role here.
This theorem that you showed is just application-based rule, right? Because this thing inside the parentheses is just the probability of sigma equals 0 divided by the probability of sigma equals 1, a given x, of course. So I guess if we multiply both sides with the probability of x.
I guess it's a couple of applications of Bayes' rule, and then you have it. It's not. I mean, it's true. So you have to be able to derive one side from the other, and a couple of applications of Bayes' rule.
No trigonometry is required.
Exactly. Okay, so we have to find the parameters, and kind of an obvious algorithm that immediately pops into mind would be this two-step approach. This algorithm would be to train the parametric model of the training versus test difference by discriminating the training data against the test data. Just learn a classifier that discriminates training versus test data, put a logistic regression or whatever on it, so just get a model of the probability of an instance being a training instance. Second, or step 1a, from this model, derive weights for all the training data, and in the next step, train the final classifier by minimizing the loss on the weighted training data. This would be something pretty easy to do, and it sort of reflects the idea of the whole thing. Then we get a classifier that is going to work well for the test data, hopefully. But this algorithm, I mean, the benefit of this algorithm is that it doesn't explicitly try to learn the test distribution and the training distribution, which, as we know from applying Bayes' rule a couple of times, isn't necessary in order to get all the correction weights. So that's good. But what it still does is it takes the original problem of minimizing the loss under the test distribution and decouples it into two problems. First, learning the difference between training and test distribution, and then minimizing the loss on the weighted data. And still the errors of both steps would kind of add up. So there's no guarantee that we find the single best assignment of values to the entire parameter vector v and w. And in order to do that, find the single best assignment for all the parameters of the system, we would need to optimize this problem. Find a set of parameters w and v that maximizes the posterior probability of all parameters given all the data that are around. And that would basically solve the problem. That would be the map hypothesis, or the hypothesis with the lowest expected regularized loss for all parameters given all the data.
The way you've written this, you're assuming 0, 1 loss, right?
No, it doesn't matter what kind of loss.
So I've lost, where in this box does the loss function show up? I'm probably missing something.
In the log likelihood. Basically, a log likelihood is the same as a loss. The prior is the same as a regularizer. So no matter, so this is just pretty generally stated, and it doesn't, this equation doesn't say anything about what the actual likelihood of the data looks like.
Yeah.
And that depends on what kind of a classifier you want to learn in the end.
So you're using the loss function somehow to skew the definition of the posterior?
The loss function is kind of the same thing as a log likelihood. And in the posterior, the likelihood, but also some prior comes into play. Let's have a look at this on the next slide. So
Yeah, okay.
This
Okay,
is,
that's good. That's fine.
This is again the integrated optimization problem of finding the parameters given all the data. And if we write this down as a log posterior, we can break this up a little bit into the likelihood of the training data given the classifier and given the model of the difference between training and test difference, the log likelihood of the model that discriminates training versus test data, V, and the log prior for the classifier and the prior for the training versus test difference model. This part, the log likelihood of the training data, given the classifier and given the difference between training and test model, can be broken up into the log likelihood of the individual training examples. And each log likelihood of each training example is weighted with this training to test training ratio. And this test training ratio now is 1 over the difference model minus 1. This is the original log likelihood of a particular training instance. It tells us how well the classifier can tell the positives from the negatives. And this is the expected number of times that the instance would occur in the training data if the training data was governed by the test distribution.
Excuse me, in this second line shouldn't this be log of probability of the training given the test, the test given training data? You have P of L comma T given B, but I think it should be P of T given L comma B. Think about the line under this log, yeah, there.
This
To the right of that. Next
The
one.
next term should
That
this
one.
be P of T given L?
D? What's D?
T given L comma B. You're generating L twice is the concern.
That's not, no, it's correct. Like this. This is the log likelihood of the classifier, and this is the log likelihood of the model that gives us the difference between training and test data. This is the log likelihood of the classifier W, and this is the log likelihood of the training test difference model. And this equation contains a number of independences. And these independences are specified by this model. Everything that has a connection is dependent, and everything that doesn't have a direct connection isn't directly dependent. So for instance, the training data is only directly dependent on the training distribution, and the test data only directly depend on the test data. And these lines connect them. But like this isn't directly connected to this and this kind of stuff. And these kind of independence assumptions allow the posterior to be broken up this way. I mean, we can go over the derivation if you like to. So log likelihood of the training data, and this tells us how many times each training instance should occur in the data. And the next term is the log likelihood of the training versus test difference model, and this just tells us how well this model can tell the training data from the test data. And then we have the, depending on how you want to see it, either priors or regularizers. If you call this a map hypothesis, these are the priors, or if you think that this is basically the same thing as a hypothesis minimizes the regularized laws, then these are the regularizers. And now how do you use this equation? In order to actually use it, you put in your either likelihood or your loss function of the classifier that you want to train in the end. And here and down here you put in either the likelihood or the loss function of the model that you use to discriminate training versus test data. And here you put in the prior on your model parameters or your regularizers. And for instance, you can do this for a logistic regression classifier. Here the likelihood is just this logistic function. These likelihoods are also the logistic function, and the priors are exponential priors on all the parameters. And this equation then can be solved basically. I mean, you can, it's an optimization criterion that you can maximize. And this gives us a logistic regression classifier for differing training versus test data, or statisticians like to call this covariate shift. In the end, this gives us a logistic regression classifier, and the primal looks like this, or the kernelized version looks like that. And the criterion from the last slide can be optimized with a Newton gradient descent. You can just come up with a derivative, with a first and second derivative, and you get a Newton descent update rule. In the primal, the update rule looks like this, and in the kernelized version, the update rule looks like that. It's not convex, unfortunately. Even though for logistic regression with equal training and test distribution, in this special case, the optimization criterion is convex, but not in the case that the two are different. There is one special case when the optimization criterion actually turns out to be convex. If for the loss functions we don't use the logistic loss, but instead the exponential loss, then the entire thing is convex, and the Newton gradient descent is guaranteed to find the maximum. And that was basically it. We are already at the experiment section, so how about any questions on the model? Anything you guys don't believe so far?
Yeah, if it's not too complicated, I'd like to see how that decomposition came about, because I was having the same problems reconciling it. So if I write down P of WV given LP, let's say I write down the joint probability and try to use your independence assumptions, I'm not sure how I would get this.
I think there must be some abusive notation here that we don't see how to reconcile yet.
No, in the first line there is no abuse of notation.
Well, if you just regard the first line as a statement of Bayes' theorem with the log and P of LT and the constant of proportionality, it doesn't go through because L shows up on the left-hand side twice.
Yes, but you have a set of independence assumptions which go into this, and then that make it work out.
Well, but you'd have to assume that L was independent of L, which it surely isn't. I mean,
No. It goes through with this set of independence assumptions.
What am I missing?
It's a proportional, so there are some terms which are not there.
Yeah, of course. You have to divide through by P of LT. But sure, but it's not the omission of those terms that I was worried about. It's that L shows up on the left-hand side twice. And I thought maybe probability that LT didn't actually mean what it occurs to me. I'm sure there's a simple answer. I'm just not saying it.
Oh, here you don't. Yes, it's probably not strong enough.
Well, maybe you can answer the
It's in
question.
the lab. It's okay.
Let's have a
Yeah, do you
pen
want to
paper
connect
and start
No,
working.
no, I mean,
Okay, let's say we'll go over it later then. Okay.
Yeah, we can do it later.
Yeah, we can go over it later. I do want to know it.
okay, here's a set of a bunch of experiments. We ran a set of experiments on spam and phishing, using spam assassin and set of newsletters as training data, and using the non-spam email from one particular N1 manager as test data, and spam emails from one particular spam trap as test data. For landmines, we were using images from one particular geographic region as training data, and test data would be radar images from another particular geographic distribution. And also we ran a set of experiments on Cora, on text classification, using elder papers as training data and more recent papers as test data. Spam, I think, is a really cool application. It works so well and it's so unsolved. One of the most popular types of spam people keep sending around these days is stock spam. They call it the pump and dump scheme. You buy worthless penny stocks of a company that doesn't really exist, place your sale order, and then send a massive wave of spam emails advertising this stock. And people have shown that actually the impact of spam on stock prices is really significant. On average, you can have a 7% appreciation in one day as a result of a stock spam mailing campaign. Isn't this incredible? So people out there base their investment strategies on the spam email that they receive. And this may lead one to the conclusion that maybe in general people aren't very smart. But then it may actually work for the first buyers of the stock spam. If you're really one of the first guys who receive these spam emails, and you know it's going to appreciate by 7% on average. So if you're the first one to buy, someone else may come later and may sell the stock from you at a higher price. So this seems to be like a you think that I think that you think that someone else is going to pay a higher price kind of thing. And it's a coordination game in which the spam emails serve as focal points, and it's of course zero sum. And the spammer has a bit of a head start because he knows he's really the first guy to know that this spam campaign is going to happen. So I mean the sum of all gains and losses is zero, and with some positive expected value for the spammer. So maybe, I don't know, maybe people aren't that smart after all. And also, scam is a nice form of email. There's a whole industry, mainly based in Nigeria, that call themselves the 419 industry. And this 419 is derived from the paragraph from the section 419 of the Nigerian Criminal Code, which is the paragraph for advanced fee fraud.
Advanced what fraud?
Advanced fee fraud. The scheme is that expecting a huge gain later, you're supposed to advance a number of fees, banking fees, or bribes to government officials, and people like this idea of getting a huge financial gain later, and are quite willing to advance a number of fees. And the more fees they have been advancing, the less inclined they are to get out of this deal. The spam senders at some point usually invite their business partners to come to Nigeria to finally sign some contracts. They have offices at the Nigerian National Bank. They must be working together with some employees at these banks, or have offices at government building and take their business partners into these official buildings in order to sign all kinds of contract and gain their trust. And when the business partner stops acting cooperatively, then usually they take them as hostage and demand ransom. And if this doesn't work out and they don't get their ransom, they in many cases shoot their business partners, and at least 15 hostages have been killed in the last couple of years. So this is a still form of spam. And phishing also very nice. It can be if professionally done. This is really quite a business model. Like if you
define phishing, I don't know what it is.
phishing means that a phisher writes a personalized email to you in order to either get you to pay for something or in order to get you to send personal information like your bank account number or your banking PIN or something. But phishing, if competently engineered, is very targeted and very hard to tell. For instance, a popular scheme would be to monitor auctions on eBay, to just keep track of who has been bidding for a product, but didn't win in the end. And then you just start sending out fake notations to everyone who has been bidding but didn't get the product. And it would just look like an eBay message: congratulations, you won the auction, it's your article, please follow this link to pay. And then you get redirected to a page that perfectly looks like eBay. And since you have actually been bidding, you're very much inclined to believe that this is the official eBay notification. And also banking emails are popular, lead you to fake banking sites that implement a man-in-the-middle attack and communicate between you and your bank, and eventually loot the bank account. And this is estimated to be a $1 billion annual business, and it's still growing, so this is really something. And also it's professionally disseminated these days. People use probabilistic context-free grammars in order to create messages, so no two identical copies of the same spam messages are sent out. Probabilistic context-free grammars are used for text messages and also for image spam. Like you get text generated from a grammar, embedded into a JPEG according to some image grammar. It's really hard to identify sort of almost identical copies, so you don't really recognize the spam batches as such. And it's pretty hard to process. Okay, back to our actual topic. On the x-axis, on the horizontal axis here is the number of test emails, the number of unlabeled emails in the user's inbox. And this is the improvement of the logistic regression classifier for covariance shift over the IID classifier. If you have just a couple of emails, then you know very little about the test distribution and the improvement is small. But as you get more and more test emails, you learn more about the difference between training and test distribution, and the difference becomes quite significant. The 50% reduction of the residual risk, that's quite a significant result. If you do the same thing, but do the optimization in 2 steps, I think that would be this curve probably. 2-stage LR would be this curve. So that's still not too bad, but not as good as doing the integrated optimization. And the Shimodera algorithm, which one would that be? This one. Shimodera doesn't really work here so well because it's really as difficult to estimate these 2 very high dimensional distributions. And also kernel density estimation in this case doesn't work so well.
Excuse me?
Yes.
So in this example, what are the features? What is X?
Back of word representation of the emails.
Do you know what is X?
X?
Is it bag of word or is it another thing?
It's back of word.
It's bag of word.
Yes.
Okay.
We were using, I think, 40,000 features or something. So it's still a relatively small space, but of course large if you want to do kernel density estimation and estimate the full density of X. So it's a 40,000 feature back of word representation.
Okay. And so could you go over what is the algorithm here in this case?
So this is the integrated covariance shift algorithm. The thing that does that solves the integrated optimization problem, learns the discriminative model of training versus test distribution, and at the same time the parameter.
So this is a linear classifier, the linear version that you showed.
A logistic regression classifier.
Okay.
So it's a linear separated with a logistic curve over it.
Okay. And so you have to update, you have to include the optimization as the...
It's a transductive setting. You need to have both the training data, the labeled training data, and the unlabeled test data in order to come up with a hypothesis and then at the same time do the prediction. So it's transductive. it's not, transductive means you need to have both the labeled training data and the unlabeled test data in order to come up with a prediction.
Right, so you're retraining every time you get a new message
Yes,
in your inbox.
yes.
Might there be, are there some cheap approximations where you could batch these training runs where you only retrain every day?
The logistic regression classifier does a Newton descent update in order to find the minimum of this integrated optimization
So you
problem.
would initialize with the
So you can keep your point and parameter space and basically just do one more Newton descent update step every time you get a new batch of emails, or every time you need to do the classification, every time the user wants to look at their email or something.
And does your training set actually change with time or not?
In this set of experiments, we had one fixed training set. I mean, these are many repetitions and it's averaged over many experiments. But for each experiment, it's one fixed training set, and the test set keeps growing.
I see. So you don't use the fact that when someone reads an email, actually is going to say if it's junk or not.
No.
No.
And I mean, even in the actual spam project, people don't really do that so much.
Okay. And what are the numbers on the vertical axis?
This is the AUC risk, the area under the ROC curve,
Yeah.
and here on the vertical axis, this is the reduction of the AUC risk. So it's 1 minus the reduction of the residual. So it's reduction of the residual AUC risk. A 50% reduction means that 1 minus AUC has been reduced by 50%. So it's 1 minus AUC of the baseline over 1 minus AUC of the bias corrected classifier, and take the whole thing and use 1 minus of this.
Do you have a question?
Yeah.
1 minus 1 minus 1 minus AUC over 1 minus AUC star, something like this.
And what is the unit for AUC?
The area under the ROC curve is the probability that a randomly drawn positive has a higher decision function value than a randomly drawn negative. So it's between 0 and 1.
Yeah, that's it. So 0.5 is unit here.
Yep.
Yeah.
Yes, the residual risk is reduced by 50%. So if there are residual, if AUC risk was 10% before the experiments, and it's 5%, 10% without the bias correction, the covariance shift correction, then it's 5% after that. But actually, it's much smaller. I mean, in spam filtering, the AUC values always look large. They look larger than it feels. This subjective. I mean, but basically, the residual risk is hugely reduced. Yes.
So far, it's only for 2 classes, classification of 2 classes, right? But does this generalize to multiple classes? I mean, the theory you talk
It's
about
not.
so far.
I mean, the logistic regression classifier is 2 class, but
I
the
understand.
integrated optimization problem, that's a pretty general formalization.
But the W would be very difficult to specify, right? For multiple classes. The prior distribution.
Yes, I mean, for multi-class classification as well as for structured output classification, I like this structured output approach, where you have a set of joint features over both the input and the output. And then you would have a set of parameters that parameterize kind of this inner product between these parameters and the joint feature representation of input and output.
That's fine.
That would be, that seems like a nice solution to me for structured prediction or multi-class.
Could you come back on what are the different curves that we see? And
This
just
is
try to
the
understand.
integrated logistic regression for covariance shift,
So which is what you described.
which is what I described.
Alright.
The next thing is this one, 2-stage logistic regression. That's the algorithm on the slide before that. First, estimate the parameters of the training versus test difference. From this, derive the weights. Assign the weights to the training data, and then minimize the weighted loss. this works this well.
And you could iterate that.
That's iterative. Oh, yeah, exactly. I mean,
It's much worse than if you do the global optimization.
it's somewhat worse, but it still works. It gives you something like, I don't know, 12% improvement or something.
Yeah, it's much worse. It's very far from
50%.
the global.
The integrated thing works better, that's true. I mean, here you have the problem that the error rate, the error that you make by estimating the training versus test difference. You do this and have some error rate, but you use this fixed set of parameters and then do something else, and kind of the error rates add up. And here you you optimize the integrated problem in one step. You don't have an adding up effect of error rates. What's the third thing? Two-stage LR for sample selection bias. That's a slightly different model. The sample selection bias model assumes that instances are first drawn from the test distribution, and then you make a decision on whether the instances are discarded or whether they are copied into the training set. This is a model that people like to use for surveys, where there is one distribution and you draw people from this distribution, ask them to fill out survey form, but then they have a certain probability of not returning the survey form. So it's a slightly different model. It works slightly differently. This one, which one is this? Is this kernel density estimation? Yes, probably. This is kernel density estimation, meaning that you first learn the training distribution by kernel density estimation, then learn the test distribution, from this derive the weights, and then minimize the weighted loss. And this guy is kernel mean matching. Kernel mean matching tries to give a weight to every training instance such that the mean value of the training data is matched to the mean value of the test data. It kind of matches the first momentum of training and test data and tries to find the weights that achieve that.
I have a question regarding all this. So one of the problems that you're trying to address is that the region where the test data lives, there may not be enough training samples, and the training samples elsewhere don't matter. How would this compare with something like a nearest neighbor classifier? Because that would indirectly get to this, right? You'd only pay attention to the training samples which are close to your test samples. So does that make any meaningful baseline? And what would it look like? Like say the 3 nearest neighbors or something. Because it has this inherent robustness in it, right? Because when you get a test sample, you'll only care about the training samples near it, which is what some of these kernel density estimates are doing.
In a way, kernel density estimation basically is the nearest neighbor classifier.
Right.
That basically is what kernel density estimation does.
Okay. No, but the thing is that then you sort of still use all the other examples with whatever weight they get under this kernel density estimation. And what I'm thinking is there might be some inherent robustness in the 3 nearest neighbors. Maybe it'll be a worthwhile experiment.
My gut feeling would be that the 3 nearest neighbor approach would be so much worse for spam filtering that still it might possibly be more robust to covariate shift, but probably still wouldn't be competitive. But I didn't actually run any experiments, so it's a valid point. Yes.
In some sense, you could think about this in a supervised learning context, and so I wonder if you thought about using like label propagation to compare against. Yeah, going after what Sanjay asked.
Semi-supervised.
Yeah, I mean, you could use like label propagation or harmonically saying.
So just to put a finer point on that question, earlier you showed a picture where you had 2 curves showing the densities in example space, but often you have the problems that label propagation is trying to deal with, as well as transductive SVM and so on, are often you look like this. You've got one thing over here and one thing way over here.
Right. Yeah. So we actually did something like this some time ago. We organized this ECML PKDD Discovery Challenge last year. For this Discovery Challenge, we had a version of the spam data set which we made available. It's still available on the ECML PKDD website. And people have been using semi-supervised learning algorithms. Actually, the transductive support vector machine from Thorsten Joachims performs quite well on this problem, and it's not so far away from the winning solution.
It's the winning solution, yours?
We didn't participate
I
in the challenge we organized. But retrospectively, we tried out some other methods and found out that transductive SVM would have been already pretty close to the winning solution when it comes to the winning solution, but correcting the covariate shift would have worked better. But no one did this for the competition, and of course we didn't really want to win our own competition so much. And we only did this retrospectively after analyzing all the solutions that have been submitted. So you can have some effect of semi-supervised learning.
So I wonder if that suggests that, I guess, covariate shift is crucial for semi-supervised learning. I mean,
Covariate shift is crucial for semi-supervised learning.
are you making a claim about semi-supervised learning?
I would rather say that if training and test distribution differ, it's crucial to make some use of the training of the test instances. And training, transductive learning or semi-supervised learning at least makes some use of the test data, even though it's, I think, not the optimal way of making use of it. I think this method is already pretty close to a pretty good way of making use for it, if training and test distribution really are not equal. And semi-supervised learning is some other way of making use to it that already gives you some benefit. That's kind of how I see it. Some more experiments with landmines, radar images used for training, one geographic region used for training, one for testing, a lot of pairwise experiments. And here, both the integrated logistic regression for covariate shift and kernel mean matching work well, and the two-stage process works somewhat less well, and the other baselines don't work so well. And text classification using the Cora corpus, using papers written on or before 95 for training and papers written after that for test. And again, the integrated logistic regression works well, followed by two-stage logistic regression, and the other baselines don't work so well here.
Why does the kernel mean matching work well for the landmines?
I think it works for the landmines because it only works for RBF kernels. For this problem, we were using RBF kernels. For the other problems, RBF kernels don't scale so well. So we couldn't really try out kernel density, kernel mean matching with RBF kernels for the other problems. And kernel mean matching for linear kernels doesn't work. And yeah, I think scaling this to multi-class classification or to structured output spaces, that would be cool. To collective classification or to problems such as parsing. I think structured output spaces are a nice way of handling these problems, and it would be nice to integrate this with the covariate shift framework. Also, with structured outputs, I mean, so far the distributions take the instances as kind of atoms. And if you have more structured output, you would have changes of the distribution that reflect certain parts of the structure. So if you have like named entity recognition, you may have an application corpus where certain types of entities just become more frequent. And you kind of want to model this distribution change within the output structures. Also, this problem can be slightly generalized, or a slight version of the problem setting that I think is really cool would be adversarial learning. It's pretty deeply also built into machine learning algorithms, that algorithms usually look at data that is generated from some system and generate a model of the data that kind of describes the system behind it. And it's, again, a pretty fundamental assumption that nature doesn't behave adversarially. So like if you learn these kinetic equations, then nature refrains from changing the laws of gravity upon noticing that you have found out the equation. And that is actually very fundamental. And in many applications, it doesn't work like this. In many applications, we have an animate nature. Nature actually observes you and does change when it notices that you managed to learn something. So it becomes a game between two adversarial opponents. Many applications for this, like the page rank used in order to rank search results. People try to find out ways to maximize this, and then search engines operators have to come up with a new hypothesis on what's a relevant search result. And Google AdWords money per click, they have to find out what's a real click and what's a faked click, and people have to find out have to write programs that make clicks look like real clicks. And also biological activities of drugs is cool. You want to predict whether some biological agent has a certain effect on a certain virus. You want to predict that, but at the same time the virus tries to come up with ways of not taking any effect from the drug. So what you actually really want to do is to come up to predict whether the drug not only is effective now, but also will be effective, given that the virus actually tries to mutate in a way that becomes resistant to the agent. A nice adversarial classification problem. And the covariance shift problem setting kind of assumes that there is a training distribution and a test distribution. But in these adversarial problems, what happens is that after each round, the test distribution gets to change with feedback to the hypothesis. So that's still slightly different, and it's a good problem, I think. So with spam filtering, the distribution gets changed based on the hypothesis. Also, I like the idea of spam over IP telephony. That's a nice problem setting. It has the same challenges as email spam. It's an adversarial problem. The test distribution keeps changing all the times, but now messages are in spoken language, and voice over IP providers are getting very interested in finding out ways to classify voice spam. That's a nice problem.
By the way, is this the kind of spam where you get messages on your answering machine at home which advertise all sorts of things?
Yes,
Okay.
but it's going to become much worse with the propagation of voice over IP, because now you can distribute spam very inexpensively, and you can do it just computer-based. You don't need any hardware. You can use botnets and virus-infected PCs in order to spread your messages in a really huge scale. So scales as well as sending spam, but fills your Skype answering machine with voice messages. So, to wrap up, learning problems with differing training and test distributions are everywhere. Whenever standard corpora are used for training, whenever distribution changes over time or is changed by an adversary, or distributions are user-specific, and the joint optimization problem that maximizes the performance under the test distribution is a good thing to maximize, and can be maximized based on the available data. The logistic regression classifier covariance shift does this, but there's quite a bunch of open research challenges around. So, thank you for your attention.
More questions?
Right, next up, thank you.
Thank you.
In one of your experiments, adding more test examples actually hurts the performance.
No, that's just
Is
noise.
that just a coincidence or exception, or
Yeah,
is
look
it
at the
like-
variance, it's just noise.
Oh, it is just noise, okay. Yeah, so in general, as you add more test examples.
Yeah,
that should-
yeah. Yes.
Yeah, what can we say about this, additional learning capacity? Meaning that how many more examples do you need to get some advantage? Because in most of the normal setting, you just don't have any additional examples for helping you. But with many test examples, of course, there are many other ways we can do this. But in terms of your setting, how many more you need for for the classifier of your complexity? Can we say something about that?
Masashi Sugiyama had a paper on error bounds for learning under covariance shift but his bounds also they depend on the training and test distribution, which are generally unknown. So I think there aren't really any error bounds that would really give you a meaningful answer to that can be actually computed based on the information and give you something like a meaningful answer to this kind of question.
Distribution free bounds are not known.
There are no bounds for which you don't need to know the distributions. Right.
Yes, another question back there. Brent. Yeah.
Yeah. So I think as Eisner said, your method kind of hinges on the fact that you have some examples in your training distributions that kind of look like the test distributions.
That's a very good point.
And that there's, I mean that there should be enough of them to actually get some learning done. So
That's a very good point. The method, the framework, and the mathematics behind it doesn't really assume it. It always works. The question is, what does it give you? Is it in any way meaningful? And what happens is that if the distributions are identical, then all the weights are constant, and you just learn from the training data. This is the optimal thing to do. If the distributions start becoming different, if you kind of tear the two distributions apart from one another, then you have some examples in the overlap that get a high weight, and some examples in the rim that get lower weights. And basically, if you completely tear these distributions apart and you have them completely overlap-free, then what happens is that every training instance gets a weight of 0. So the likelihood of every possible hypothesis is 1, and you're just learning from an empty training set. So only your regularizer determines the hypothesis. But I mean, this makes perfect sense. If your training data has no information about the distribution, you are trying to learn from an empty sample. So it all works. Like you can learn, like you can do a logistic regression classifier from an empty sample, but it's not going to be very helpful.
That does lead to a second order question though, which is, once you do the covariate shift-based learning, can you then assign a confidence, like a probability of correct classification? Because I would hope that in the first extreme you would have high confidence, in the second extreme not only would you be learning essentially from an empty training set, but you'd also know that your probability of error on the test data is very high.
Right.
So
but
that
would that be specific for the learning under covariate shift case, or couldn't you do this like you do it for any other classifier?
No, you would, but what I'm thinking is whether the scaling would provide you a better hook on that. Whether you would know from how you...
I mean, you would have an idea of kind of if the effective size of your training set, and that would have to go into the confidence estimate. If you do a logistic regression, you can always get something like a confidence estimate, but now you have to take into account that your effective sample size is somehow reduced. I guess you could do it probably.
That I'm actually
requires
also
some
thinking
thinking
that
about it,
you
I would
had
say.
this parameter set V which classified how close or far away you're from training. Whether that wouldn't give
Well,
you
that would give you a bound
either a bound or at least
or confidence.
some region saying this is in
It's a
V.
good point.
So you're saying that if, for example, all the weights are very low, if all your training data doesn't look at all like your test data, probably you can say with some confidence that your confidence measure is going to be low.
No, there was a sigma of, there was a
Yeah.
probability distribution sigma given X,
Exactly.
and that can be computed for the test examples as well.
Yes.
Yeah.
And what I'm thinking is, unlike standard classifiers, whether in this case, because you estimated it jointly with W, whether that wouldn't give you a better estimate of your probability of error, knowing that this is very far away from your training samples versus.
Good point.
Because you can always do the standard thing, but here you optimize V jointly with W.
I see.
Okay, Fred,
You had in the section of future work, you had parsing. So do you actually have a hope that one could learn from Wall Street Journal, Tree Bank, correct parsers for switchboard, let's say?
I don't know. You guys have the domain knowledge about parsing.
Well, it seems enormously complex. I mean, it
The
would be
question here
very
might be structure.
It would be very desirable because, as you say, English is English, and even though people who speak spontaneously kind of get on weak ground, it's still English.
I think once you partition the space so much, it's
Yeah.
hopeless. So if you have to go so many levels of details, then
I
it's
can imagine
hopeless.
that you can use the structured output approach and integrate this into the covariance. As for the expected empirical results, I don't really feel very confident about making a conjecture about how well this would be working. I have no idea.
But you had something about part of speech there.
Yeah.
Have you tried that?
No.
Because that's of course much simpler.
Yeah. But we haven't done this integration of the structured output into the framework at all.
So you mentioned that actually for the logistic function that it's not convex when you do this. So is it actually expected, or the exponential loss that you're using?
For the exponential loss, it's convex, but all the experiments that's convex thing, that's a pretty recent result.
I see.
And these experiments are slightly older. They're all done with the logistic regression classifier on the non-convex optimization.
So it's not necessarily optimal.
It's not necessarily the global optimum. Actually, the more test data you have, the smoother is this optimization function. If you have very few test data, like in particular for this problem, the exponential loss works a lot better. This function has very many local optima. It's a very tricky optimization problem, and here the exponential loss gives a substantial improvement. But for the other problems, for this one, right, for the landmine detection, for this one, there are very many local optima, and exponential loss gives a huge benefit. But for the other ones, like here, this is most likely this already is the global optimum, and exponential loss doesn't give any benefit. Depends a lot on the problem whether there are local optima or not.
I mean, it's not a big trend, but there is a trend in the solid line for the error bars to shrink a little bit as you go to the right. I mean,
it could be noise,
yeah.
or it couldn't be. If it's not noise, then my explanation would be that it has something to do with the number of local optima in this optimization problem. Maybe it develops unfavorably. For the exponential loss, there is no negative trend. There is less noise, and there's no local optimum. So for exponential noise, the trend is the opposite.
David, did you have a question? No? Do we have any other questions? All right, before we thank our speaker, I want to announce there will be lunch in about 10 or 12 minutes out in Barton, so everybody's welcome. And also, along with the speaker, I want to thank Erin Fitzgerald. Erin has helped us do the videotaping. It turns out our video services doesn't have anybody to do this for us this summer. So students will be volunteering, and I thank her also. And of course, we thank our speaker.